to teach. We are basically just going to learn one thing in this class. We're going to learn how to calculate forces between objects, reaction forces. And we're just going to do repetitions over and over and over again. But there's a lot of different types of problems, so we'll learn how to deal with a lot of different situations. Today, I'm going to go over the syllabus. I'm going to give a little overview of statics, show you some examples of the types of problems that we're going to work on. And then I'll go through this vector review. Who's been to D2L already? Okay, so on D2L, I put up a vector review. Looks like this. And there are 11 practice problems on the back. And as I go through the syllabus, I'll explain the thing with problem sets versus practice problems. But you don't have to go through this. A lot of you are probably, this will be a little unnecessary. But I would say look at the practice problems on the back and make sure that you're comfortable with those types of problems. The nice thing about this review is it's not all about vectors. It's just the vector stuff that we're going to do a lot in this class. Okay, so it's in a nice, concise, I think it's 6 pages or something. Okay. Let's see. So first, the syllabus. Let's see. Come on. This will be riveting video.
Can you add music to it?
Yeah, I guess this part I will, yeah. Ah, there it is, the syllabus. Okay. So, the class is statics. It's 3 credits. There's no lab or anything, which means that if you want to, aside from exams, you're welcome to treat this totally as an online class. If you feel comfortable just watching the videos, you can do that as often as you want. If you want to turn in problem sets via the Dropbox in D2L, that's all right with me. Although I'll go into later how sort of convincing me that you're putting in a consistent effort throughout the semester is a small part of your grade, a very small part, but so if you're never going to show up at class, you should give me a call every once in a while or something, make up a question. You know how, when you have to ask questions, so you make up some question you already know the answer to or something. Just do stuff like that. I fall for that stuff. My name is Guy O'Lakin. My office is S1322, right between the 2 labs. There's my email, my phone number. To get a hold of me, email works best. I try to return phone messages, but email is like sitting right there. So if you can ask a question by email, please do that. The prerequisites are the first semester of engineering physics and Calculus 2. And by the way, Calc 2 is sort of just on there as a, I mean, I guess there are maybe a total of one full class period that will be using integrals. But other than that, the calculus requirement is just for sort of mathematical comfort, you know, like the math, the level of the math is going to be really simple, but you're going to need to be comfortable with it. Really, the only math that you're going to use this whole semester is vector manipulations. The hard part of this class is going to be figuring out, you know, how to draw accurate free body diagrams of these complicated things, how to keep straight what forces are on what body. That kind of stuff just becomes a bookkeeping problem when you start dealing with a lot of bodies or breaking a body up into a lot of parts. So that's the main thing that this course is about. Oh, and co-requisite of differential equations. That is easily waivable. Okay, so the things that we're going to try to do in this class are first, we're going to, the physical quantities we're going to deal with are vector quantities, forces, and moments. You know, I'm sure that it's been brought up in classes before, but problems are so much easier to write in 2 dimensions than in 3 dimensions that you tend to forget that moments are vectors, you know, because in 2 dimensions, a moment always acts in the same direction, right, out of the page or into the page. So you can represent it just with a scalar value, but really in 3D, moments are vectors just like forces are. And so when we do Newton's second law, that's a vector equation. When we do the rotational version of Newton's second law, m equals I alpha, that's also a vector equation. We're going to deal with a lot of vector calculations. We're going to learn to calculate centroids. We're going to learn a very specific approach to drawing free body diagrams and using Newton's laws for multi-body structures. And then near the end of the class, we're going to start to talk about internal loads. So, and really, in a way, it's just, it's sort of interesting to know that there's nothing fundamentally different about calculating an internal load versus a reaction force or a reaction load. If you treat this pen as your free body, right, then a force between this part of the pen and this part of the pen is an internal load, right? It's inside your free body. But if you only treat this half of the pen as your free body, then that force that this side is applying to this side is an external load, and the calculations are exactly the same, okay? But we're going to learn a systematic way to approach calculating internal loads. And what do you think the benefits are? Like, why do you think you calculate internal loads?
So you don't have the 35 bridge collapse again?
Yeah, that's right. It's to try to predict fracture of some kind, you know. You want to figure out what the loads are that are acting on some part of this pen, say, like if this was holding up the bridge. You'd want to calculate where are those loads going to be the greatest. Where is this thing most likely to fracture? And can this plastic, you know, whatever it's made out of, handle those internal loads that it's feeling? The necessary materials. There is a textbook. You really won't need it for this class, but it is a good idea for all of you guys to have a statics book on hand, like for future classes. So I think it's fair to think of it as required. But the thing that that you should that you might want to think about is we're not going to do any problems out of the book, so you don't have to have the most current version. So if you can find it on eBay or something, like a 7th edition or an 8th edition or something, and get it for 20 bucks instead of 150 bucks or whatever it is, that's a great idea. And we also are going to use a graphing calculator. It says on here, preferably one that computes eigenvalues and eigenvectors. The TI-89 does that. That's not really for this class, but that's just something, if you haven't bought a graphing calculator yet, that's something you might want to consider. That'll come in really handy in future classes. So the topics that we're going to cover, we're going to start with this vector review. That's just going to be today. Then we're going to talk about particle statics. So what's the difference between, let's see, what's the difference between particle physics and rigid body physics? So those are kind of the two things that we're breaking it up into. So particle physics, we're assuming that we're treating an object as if it has no size, okay? So there's no such thing as moments. Every force we treat as acting through the center of the object, okay? When you go on to dealing with rigid bodies, you assume that this thing has a size. And so if you think of like a car or something, a big force applied at the end of the car causes rotations, whereas that same force applied through the center, the center of mass of the car, only causes an acceleration, a linear acceleration. So basically, when we talk about particle physics, particle statics, we're only going to be dealing with forces. Okay, we're not going to be dealing with moments. Then we'll go on to rigid bodies. We'll talk about equilibrium, which is the entire, subject of this entire course. And then we'll go from single body equilibrium to multi-body equilibrium, where we're going to talk about simple machines and frames and trusses and that kind of thing. And then we will talk about internal loads in beams and cables. Internal loads in cables is pretty simple, but in beams it's more complicated. And then finally, hopefully we'll get to friction. But actually, it's interesting to notice that in statics, friction is not a very complicated topic because friction opposes motion and we don't have any motion, so it's so friction is something you have to consider in statics, but it's just sort of an either-or case. Like, is this friction, is there enough friction here to prevent movement? And if there is, then you do it as a statics problem, just like we'd been doing. Okay. Oops. Okay. So here is how assignments and problems are going to work. About once a week, I'll assign practice problems and problem sets. The problem sets you have to turn in. The practice problems you don't have to turn in. The practice problems are going to be very much like the exam questions. Okay, so you could skip those, but that would be a terrible idea, because if you are really comfortable with the ideas in the practice problems, you'll be able to walk into the exam basically and fill it out, maybe not that simple, but there's not going to be any real crazy paradigm shifts happening on the tests, The problem sets are going to be a little different because you have an amount of time to work on them. You're not doing it under the gun in a timed setting. So those are going to be, it's not going to be very many problems, probably 1 or 2 problems a week, but those are going to take a little bit more overall, like big picture thinking. And there are going to be times when you are going to have to read a problem and reread it and then try something and it won't work and try something else, okay? That won't really be the case with the practice problems. The practice problems are kind of just drills, you know, in a way, just getting familiar with the concepts. Um, and because the practice problems are pretty just sort of based on the fundamentals, and the assigned problems are going to require a little extra thinking besides those fundamentals, the pattern you should get into, if it's when it's possible, as much as you can, is do the practice problems when they're assigned. About a week later, I'm going to give you a problem set that's on those same ideas as the practice problems. So get those practice problems done for the first time before you go to the problem set, okay? And by then you'll have those fundamentals kind of drilled a little bit, and that'll give you the ability to think a little more creatively on the problem set problems, okay? And then, like before the exam, when you're getting ready for the test, do those practice problems again. You know, at least, I would say at least do each one twice. And you'll feel comfortable for the test. What was I going to say? Oh, I know. So I think I probably don't need to tell you guys this as much as I had to tell like the physics class this, but you don't want to study the practice problems, like read the practice problems and read the solution. I've had people come and talk to me and not understand like why they haven't been doing so well on the exams, and it turns out that's what they were doing with these practice problems. Like read the problems, read the solutions, read the problems again, read the solutions. Actually do the problems, you know, and then look at the solutions and figure out what you did right and what you did wrong, you know. Then do the problems again, you know, maybe a week later or something. Look at the solutions. That's the way to take advantage of these. And hopefully that'll just sort of beat it into your head. Yep.
Where are the problems coming from?
I'm writing them all. And so on the problem sets, I'm not going to give you solutions for those, but I'd be happy to, you know, after the grades are done for that problem set or whatever, I'd be happy to go through the solution with you. But the practice problems, I'll always get the solutions up as soon as I can, so you always have those on hand. The grading is most likely just going to be 90% A, 80% B, and down the list. I might relax that a little bit. But the only reason I would relax that is if, like say I gave an exam that was just a lot harder than I meant it to be and the class average was 50 or something, then I'm not gonna give grades so that the highest grade in the class is a B or something like that. Okay, so if something happens and the grades are too low, I'll curve it a little bit. But I'm not going to go the other way. So if I give an exam that the average score is a 97 or something, then that's your good fortune, you know. So if you have a 90% or an 80%, you know that you have those grades, okay? But you might get bumped up a little bit if there's like an exam or an assignment or something that people do especially badly on. Your grade for the class, so that 90, 80, 70, 60, is based 70% on exams, and there's going to be 3 of those. Oh, and I just noticed.
That's 17.5%.
That's right. So one of those things is wrong. It says 3 total and 70.
Was there a final in there too? Oh, the final exam 4.
Okay, I know I had this all figured out. Okay, so yeah, 4 exams total. And that final is not going to be a cumulative final. It's just going to be like the 4th exam. So yeah, that's a mistake where it says exams 3 total. What? No. Okay, so I'm doing the with like dropping exams and stuff. I'm doing it a little different than in the physics class. So I'm trying to remember. So I think no, I think I just put that 3 there and then changed my mind. I think it's 4. You're going to get scored on all of them, and the 4th one is just during the finals period. So the dates of those exams are all given. So you might want to look at that schedule and make sure you can make it to those. What?
What's the final? Do you have the date on that?
Well, they do have like a sort of a tentative date, but they always change it late in the semester. But it's in the class schedule, on the last page of the class schedule.
So the final is weighted the same as every other test.
That's right. Yeah. And it's just on, the material since exam 3. It's not going to be over the whole semester. And it's only going to be an hour and 20 minutes long. It's just going to be exactly like the other ones. If one of those dates doesn't work for you, let me know as soon as you can, okay, and we can work something out. Okay, problem sets, the other 25% of your grade. So, you've had problem sets before. The one thing I want to talk about is I want you to work with each other. Like, that's a great thing to get used to doing. That's something graduate schools and the university and employers really want students to be comfortable with. But that causes, a little bit of a problem because I'm grading you individually. So there has to somewhere be a distinction between what's working together and what's copying someone else, right? So this is the distinction to me. And I think this makes pretty good sense. Let me know if there's something you don't understand about this. But basically, what you turn in has to represent your own understanding of the material, okay? That understanding, if that comes from working with someone else or even someone else explaining it to you, that's perfect, that's great, But you have to have enough of an understanding that you can, after you work together, go off by yourself and write up the paper that you turn into me, without like looking at your notes and writing line for line. Okay, that's copying. If someone explains something to you or you figure something out together, and then later you take those notes, go back to whatever, and write out the paper that you turn into me, that's getting an understanding from group work that then you show in your paper, and that's what I want to see. Okay, is anything confusing about that? Okay. So the assignments are due at the beginning of the lecture on the due date that I give you, just so like I don't want people in here finishing their assignments while I'm talking. It'll probably be a little less than once a week that you'll get a problem set. There'll probably be a total of like 10 or 12 assignments. And of those 10 or 12 assignments, your lowest score is going to get dropped in the grade. So one time you can not turn one in or turn in a crummy one, The homework is just going to be graded 0, 1, 2, 3. So it's going to be a pretty basic grading scale. 3 out of 3, you can think of that as sort of A/B work. You know, like you pretty much did the assignment the way it should be done. 2 out of 3 means you put effort into it. For the most part, it's good, but there are, to me, what I consider to be fundamental misunderstandings in one area or more in the assignment. 1 out of 3 means you kind of slapped it together at the last minute, you know, and 0 is not turned in. And every class period that the problem set is late, it'll get bumped down 1 point from what it would have scored. Okay, so if you, 1 class period late, you turn in an assignment that would be a 3 out of 3, the score will be a 2 out of 3. Okay, but I don't think I'm going to go negative. So, like if you turn in a poor quality assignment like a week late, that would be a -2. I think I'll just go ahead and call that a 0. And that also would mean that like every time you didn't turn something in, your 0 kept going down, you know? So let's not do that. Okay, participation. So I said that that's worth 5% of your grade, right here. Really, so the 70% and the 25%, those are calculated, you know, like numerically that's what they are. This 5% participation score you can just sort of think of as like a fudge factor. Like if I hear from you a lot, you always ask questions, you come to office hours, your assignments, you know, are always show a lot of effort, I'm going to be more likely to bump up a 88 to a A, basically. You know, if you sit in the back and every time I, you know, miss a negative sign on the board or something, you're like, that's a negative, you idiot, you know, like I don't like that. And if you get a 89.94, that's a B, you know. Mike, I'm talking to you. There's going to be a change this semester. So that's the idea with participation. General policies and comments. I don't take attendance. I mentioned that before. So if you like watching these lectures on video instead of coming to class, or it's more convenient for you, feel free to do that. Just make sure, like, recognize that there is a strong tendency to tell yourself you're going to watch the video and then not get around to it, or not take it seriously, or not take notes on it when you watch it. When you watch those videos, you have to treat it the same way you would treat being in lecture, or else you're getting less out of it, you know. But I've had students, like I did deform that way in the spring, and where actually deform is a totally online class. So there were no lectures. People just watched the lectures on video. And I had people say that they liked being able to, like if you missed something, to rewind it and watch it again. And people also said they liked being able to watch half an hour and then go get a cup of coffee and come back and watch the rest. So there's some nice things about it.
Is it the same? Do you do the same for next semester?
Yeah, I think so. Oh, in deform.
Yeah.
Yeah, I think I am.
I think that would probably add a couple of people to it.
Yeah, hopefully. We'd love to, you know, start getting people like remote, you know, people off at other campuses or whatever to take deform online. I was like all gung-ho to do, since none of them are lab classes, I'm like, let's do deform and statics and dynamics all online, you know. But Julie was sort of the voice of reason, like, let's wait a while and see how it goes before we jump in too hard, you know.
Yeah, I feel like you kind of care about your students.
It's not true. That's a common misconception. No, no, I'm just kidding. So all the material for the class is going to be posted on D2L. So get in the habit of going to D2L maybe every day. Just check, look in the news thing and see if there's anything new posted on there. And anything like as we go, the new stuff that I post, I'm going to bookmark. So you'll have links to the new stuff right on the main screen. I would show you what the D2L page looks like, but then I'd have to change my password again. And you guys, I think number 3 is more for the 18-year-old students in my college physics class, you know, who are like, whoa, man, treat each other respectfully. But you're sort of used to the drill, you know, so. But yeah, please don't talk to each other at full volume while I'm talking. And I guess one thing is, you know, with these lectures posted online and everything, if there's a day where you don't think you can keep your eyes open or whatever, sleeping or not paying attention or whatever just sort of detracts from the class atmosphere. So I would rather if you just stayed out of class that day, watch the video lecture, and then the people who are in class, we can keep sort of an energy level, you know, like an atmosphere of caring about what's going on. Okay? So that's all for the syllabus. Anyone have any questions about any of this? All right. So let's talk about what statics is. And then this will be sort of a short introduction. Now you need to start taking notes. And then we'll get into the vector review after that. So statics is meant to be your first mechanics class. I guess there's actually a couple people who took D-Form with me last semester. That's usually not the way to go, but if you've already been through D-Form, statics is going to be a lot easier, I suppose. It's your first mechanics class. And by mechanics, I mean what loads are acting on a body or a collection of bodies. And maybe more specifically, will it break? Will the object be damaged? And so statics is sort of about calculating the reaction forces that act on a body, whereas D-Form, we're looking inside the body at what are the internal loads, and we talk about stresses and strains, which are just sort of detailed ways of describing those internal loads. Actually, so what does static mean, first of all? Not moving. And the class is called statics, but the fact that objects are static is not really the key to this class. For example, if something's in static equilibrium, Newton's second law and the rotational version of Newton's second law look like this. The sum of the forces is equal to 0, and the sum of the moments about some point, I'll say A, is equal to 0. Okay? And these are the fundamental equations in this class. Okay? everything we do is going to be based on solving these equations, setting them up the right way. So how different would it be if you have an object that's moving? So say you have a dynamic conditions. Then you just have this. Right? You just have to calculate that acceleration, A, and that angular acceleration, alpha. The key, the real key, is learning to use, so I'm going to use this abbreviation all through this semester. I'll call this Newton's second law. And I'll call this one the rotational version of Newton's second law, Rn2L. Okay. The real key is to learn to use these equations, N2L and the rotational Newton's second law, to calculate reaction forces. And the methods that we're going to learn in this class would apply just as well to this dynamic condition as it would in static conditions. Okay? It's just that you have to know a little more about what's going on. You have to be able to calculate the acceleration and angular acceleration. So here is the type of problem that we're going to do. We're not going to jump right in with this kind of problem, but this is what we're going to get to by like the middle of the semester. Did we do this in intro when you were in it? Okay. We don't do it anymore in intro. Okay, so this little clamp thing is used in surgery. So you use it to hold on to tissues or to clip things in some cases. So this is unfortunately for somebody a piece of a bone. And you apply forces here. Call that F1 and call this F2. And you want to know what forces are being applied to this segment of bone. Like say you're designing this piece of equipment. And notice that you can't do this problem with you can't solve this problem with a single free body diagram and a single application of Newton's second law. You're going to have to isolate possibly the whole thing. Often you're going to have to isolate the whole thing in addition to treating this as a free body, this as a free body, this, and so that's the kind of thing that we're going to be working on. Another example, one that maybe isn't as obvious as an engineering problem, but it's the kind of thing that actually I did during my master's. My master's was in biomedical engineering. Say you have a diver standing on the edge of the 10-meter board. We'll treat, it's hard to draw on this thing. So we'll treat the body like this. Random line into the top thing. But so say this is all, we'll just treat the upper body as, that looks horrible. Okay, so say that's, we know where the center of mass and stuff of the upper body is. By the way, has everyone seen that symbol before? You know, that little symbol I just drew, that doesn't mean he's nuclearly reactive. That means that where the center of this circle is the center of mass of that object. And so like in car commercials where the crash test dummies are driving cars and stuff, and they have these things all over their body. They have one on their head, one on their torso. That's on there so that from the videotape, you can tell where the center of mass of those objects is, and then you can go back and do the physics of what the forces are that they're feeling. It's kind of interesting. Not super interesting, but. Okay, so say you want to calculate what are the forces that the tendons, like the Achilles tendon, is feeling standing up in this position. Okay, so maybe I'll draw it as a cable. That's a pretty reasonable description of what the Achilles tendon does, and the muscle it's attached to, the gastrocnemius. So even though this isn't a collection of engineering materials, this is, you know, a human body, we can break it up in a way where we can treat it the same as we would engineering materials, like assume this segment that makes up the lower leg is a rigid body, assume the segment that makes up the thigh is a rigid body, assume they're connected by some kind of pin joints or in 3 dimensions by a ball and socket joint or something, and just calculate what the forces are for this diver to be in static equilibrium. Then you could do the same thing, calculate what forces you'd need for a certain acceleration if you just switch from these static conditions to these dynamic conditions. And then, you know, the last one, say this is the frame of a bicycle. And this frame is loaded by some force here coming from the fork, some force here coming from the handlebars, some force here coming from the seat, pedals, F3, and the back wheel. And you might want to know, where is this frame susceptible? Oh no, now I have to spell that. Let's go with likely. Where's this frame likely to crack? Okay, so those are all questions that we'll be able to answer based on this class. And what we're going to see is you can treat all 3 of these cases as exactly the same type of problem. The book actually breaks problems up into a few different types. It breaks them up into trusses, frames, machines, probably some other ones. I'm going to go into that briefly, but really what I'm going to do more, what I'm going to try to emphasize is that, okay, let me back up. So why do they do that? Why do they break it up into trusses and frames and machines? Because if you treat each one in its own way, you can simplify some things about it. Okay, like you can take advantage of what a truss is and simplify the math a little bit You can take advantage of what a frame is and simplify it a little bit, and you have to simplify those in different ways. But if you're not interested in simplifying the math, you can treat them exactly the same. It's all based on the same fundamentals. And so I'm going to emphasize the sort of non-simplified overall way that'll work in any problem you ever see, okay? Because the reason that I'm going to do that is nobody anymore in the 2000s does truss calculations by hand. You know, you write a computer program to do it. And so, like, the benefit of cutting down from a system of 20 equations to a system of 8 equations, that used to be significant. Now it's not, you know. So I don't think it's really that necessary for you to be really good at calculating trusses by hand and calculating frames by hand. What's really important is that even if it takes a little bit longer, you can look at any problem of any type and solve it, you know, and eventually write a computer program to solve it. That's where we're trying to go with this. So, in a sense, like what the book calls, I don't know what chapters they are, but let's say the book calls it chapters 3, 4, 5, and 6. To us is all going to be essentially one topic, okay? And that one topic, we're going to just get tons and tons of reps, you know? We're going to do problem after problem after problem, and like, I dare you to try to forget how to do this. Any questions about that? Sort of, that was supposed to be an overview of where statics fits into your whole list of courses that you're going to be taking. Okay, well, let's move on to a little vector review. Like I said, there's a document on D2L. I'm not going to go through the whole thing. I'm going to leave some of the basic things out. But if you want to go back and review more in depth than I'm doing right now, just go back and look at this document on D2L. Okay, so this is a vector. It lives in math land, but we pretend it lives with us, you know. So maybe we'll say this has a length of 1.5 meters, and it makes an angle of 30 degrees with the ground, okay? Okay, so that's what a vector is. And no matter who's looking at it, it's still angled at 30 degrees from the ground. It still has a length of 1.5 meters, right? So if I look at it sitting here, it looks one way. If I look at it sitting here with my head like this, it looks a different way, but it's still the same vector, right? What do I need in order to represent this vector in terms of coordinates? I mean, I know, like, mathematically I'm going to use trig functions and whatever, but that's like, what else do this is not enough yet for me to express this in coordinates. What else do I need? A coordinate system, that's right. And a coordinate system is made up of an origin and an orientation, okay? So this is what a vector is in its most sort of fundamental form. But to represent it, as coordinates, you need to specify a coordinate system. Once you do that, you have a 2D vector that looks like this. or a 3D vector that looks like this. And really, they're the same thing. Okay, keep that in mind, that this is just equivalent to x, y, 0. Okay? So keep in mind that any 2D vectors you can do as a 3D calculation by just setting the third component to 0. Okay? Once you have your vectors as components, there are a few calculations that we're going to want to do over and over again. So to multiply a vector by a scalar, so say that C is a scalar and your vector is x, y, z. You just multiply each of the components by C. So you get Cx, Cy, Cz. To add two vectors, so let's call it Ax, Ay, and Az, and add that to Bx, By, Bz. You just add the components. So Ax plus Bx, Ay plus By, Az plus Bz. Those I'm sure you've done so many times that you'll never forget that. How about calculating the length of a vector? So say that you have a vector v that's equal to Vx, Vy, Vz. Okay. Then the length of that vector v is Vx squared plus Vy squared plus Vz squared square root. Okay, and this is the notation with the absolute value sign. And you can see that from this definition and thinking of that vector v as like to think of a 2D vector, just think of it as having the z component equal to 0. You can see that what would happen if this v was a 2D vector? You just have a Vx, Vy, 0. Okay, so when you calculated that length, you just have Vx squared plus Vy squared square root, right? You just, this Vz squared would be equal to 0. Okay, so this is totally generalizable to 2D. This formula works for 2D as well as 3D. Okay, another very important thing is calculating unit vectors. So if you think of a vector as a direction and a magnitude, right? That's the information conveyed by a vector. You can think of a unit vector as just a pure direction, okay? Then, so a unit vector is like a unit vector in the direction of a given vector is in the same direction as that given vector, and it's divided by the magnitude of that given vector, so its length is equal to 1. And then if you want to give it a length of, you want to give a unit vector a length of 40 or a magnitude of 40, you multiply it by 40. Okay, so you can think of it as a pure direction, and we're going to use it all the time. So say again that you have a vector v that's vx, vy, vz. Then the unit vector in the direction of v, and we denote it v hat, is equal to, in its most concise notation, 1 over the length of v, and notice that's a scalar, 1 over the length of v, times the vector v. Okay, so you can think of that, you can rewrite that as vx over vx squared plus vy squared plus vz squared square root, that's the first component, vy over that same square root, and then vz over that same square root. And that's your vector. Okay. The most common case where we'll use this is for calculating cable forces. Okay, because a cable force can only be tension, right? So we know the direction of a cable force. What we don't know a lot of times is the magnitude. Like, that's something we have to calculate. And if we treat a cable force like the force a cable applies, so say that you have this object here, and you want to calculate, let's make it possible. So say that you have this object that's connected to the wall by a pin joint, and it's supported by this cable, okay? And you want to know what the force is in this cable. What's the force the cable applies to the object? Well, the cable is going to apply a force vector, right? So your first reaction might be to represent it as an unknown vector v, right, with an unknown x component and an unknown y component. But the problem with that is we know more than that about the cable, right? We know the direction that it acts. The only thing we don't know is the magnitude of that force, right? And so there must be a way to represent that unknown force vector with a single variable, okay? Does that make sense? You know what I'm talking about? So let's call this point A and this point B. We don't want to just use, say, Vx, Vy, or sorry, let me change that to Fx, Fy. So you know it's the force we're talking about. because that's two variables. And to solve two variables, you need two equations, right? And equations in statics and any kind of mechanics are very precious. You know, you can't just find unlimited equations on the equation tree. So anytime you can cut down the number of variables, you're making it more likely that a solution can be found, okay? So what you need to do is we'll calculate the vector pointing from A to B, okay? Because we know the force vector acts in the direction. Oh no. Dang it. Let me just sort of draw what I'm talking about up here. Okay, so we know the force that the vector is going to apply to this object acts in a direction this way, right? We know the force vector looks like that. We just don't know what the magnitude is. So what I'm going to do is calculate a vector in this direction, okay? Once I have that vector, I'm going to calculate the unit vector in that direction. And then I'm going to multiply that unit vector by the single unknown, the magnitude of the force, which is the cable tension. And that's going to give me a variable that only has a single unknown, say the tension T, and still represents a full vector, okay? So okay. Okay, so we know that the force vector acts in the direction from A to B, from the point A to the point B, right? So I'm going to define this vector equal to B minus A, okay? And let's, just to illustrate what I'm talking about, let's define A equal to 1, 1, and B equal to, just so I can do it in my head, let's do it as 2, 2. Okay? Notice that makes sense with the picture, right? So this vector V is B minus A, so 2, 2 minus 1, 1 is equal to 1, 1. So that's a vector pointing from A to B, but it has a length different from 1, so now we want to turn that into a unit vector. So V hat is equal to 1 over 1 squared plus 1 squared square root, so that's the square root of 2, times the vector 1, 1. And if you multiply that out, you get 0.7071, 0.7071. And now the force applied by the cable is just the unknown cable tension, T, times that unit vector. Okay, so we're going to use unit vectors for things like that all the time in this class. Any questions about that? Did that make sense, the thought process there? All right, so now the last couple things I want to talk about. We already talked about multiplying a vector by a scalar, right? Now I want to talk about multiplying a vector by another vector. And there's two ways to do that. So multiplying two vectors together. The first way is the dot product. And the dot product produces a scalar. You take two vector values, dot product them together, and you get a scalar out. And so it's sometimes called the scalar product. It's also sometimes called the inner product because it measures how close two things are to being in the same direction. You can think about the definition of it and sort of figure out how that works. You know, it's a projection of one thing onto another thing, sort of scaled by their relative lengths. So if you have a vector ax, ay, az, and you dot it with a vector bx, by, bz, you get the scalar value ax bx plus ay by plus az bz. Okay, that's a scalar value, just a single number. And notice that if you're doing this in 2 dimensions, this formula works. Az and bz are just equal to 0, so your last component here is equal to 0. And notice the dot product is 0 for 2 perpendicular vectors. It has its maximum positive value for 2 vectors in the same direction. And it has its maximum, its greatest negative value. Maybe I should say that. Largest negative value. For 2 vectors in opposite directions. So they're parallel to each other, but the heads are facing the opposite directions. The second type of vector product is the cross product. And if you have two vectors, AX, AY, AZ, and you cross it with a vector BX, BY, BZ, you get a vector out this time. And that vector looks like this. AY, BZ minus BY, AZ. Then AX, BZ minus BX, AZ. And then, like, when you take linear algebra, you work with vectors, you notice, like, Y always has to be difficult. Like, it can't ever go along with the crowd. It's really annoying. It's a personality trait that is really frustrating. But so, yeah, Y, it sort of follows the pattern, but it has to be negative of the other two. And then the last one. So you sort of notice the pattern that develops here, like if you're trying to remember this. The X component of the output has no X. It only has a Y and a Z. The Y component of the output doesn't have a Y. It just has an X and a Z. And the Z component doesn't have a Z. It just has an X and a Y. Okay. So there's the formula. And what happens if you have two-dimensional vectors? You're taking the cross product between vectors with 0 Z components. Well, look at the outputs X and Y components here. You have Z components in every term here. So this all is equal to 0, right? You have Z components in every term here. So this is all equal to 0. So if you're taking the cross product of two vectors that don't have Z components, that cross product is always going to only have a Z component, okay? And that's why when you do 2D moment problems, 2D rotational problems, you calculate the moment as a cross product, and that's why your moments are always they always act only in the Z component, only in the Z direction. And that's why you sort of forget that they're even vectors at all, because you can just sort of treat them as numbers. So notice with the cross product, the output is always perpendicular to both of the two input vectors. And which direction it is, right? So say you have two vectors here. What's a vector that's perpendicular to both of those? There are two of them. There's one here and one here, right? And how do you know which direction it is? The right-hand rule, right? Whoops. So I'll say according to the right-hand rule. And also notice that forget that one. Okay, let's call it a day. Anybody have any questions about anything we talked about?
Can you go back a page?
Yeah. You just didn't get it, like all. Okay.
I got class here right now.
Right here, right now?
Right here, right now.
Kidding me.
No,
What do you have next?
I got circuit.
Hmm. How is that? Also an hour and 20 minutes?
No, that's
Oh.
just an hour.
Oh, that's good.
I remember that being
What's that?